Hello everyone, my name is Baoyue from Beihang University. I will go through the presentation of our paper, revisiting the design of LSM-tree-based OLTP storage engine with persistent memory. LSM-tree-based storage engine has been widely used in today's OLTP databases. The LSM-tree achieves fast writes and high compression for data levels. However, there are still several problems for current disk-oriented designs. The first is the high write overheads for synchronous war logs. These logs are necessary to guarantee ACID transactions. The second one is a problem for level 0. The tiered compaction in level 0 delivers faster flashes, but results in large read amplification. In fact, this is a design trade-off between reads and writes. The third problem is the recovery overheads incurred by volatile DRAM Memtable. More records in Memtable brings high performance, but results in more recovery time. The emergent persistent memory gives us new opportunities to address these problems. Multiple challenges exist to use the new hardware, such as the high overheads to guarantee persistence and atomicity, and the performance differences for different access patterns. With these challenges, we will answer for the questions. First, how to design efficient persistent Memtable to replace the DRAM for fast recovery. Second, can the war log be removed to achieve fast persistence? Third, can the tiered level 0 be replaced with one in larger capacity PM? Last, how to efficiently manage the persistent memory allocation, avoid persistent memory leaks, and reduce persistent memory fragmentations. Addressing these questions, we designed 4 components: the semi-persistent Memtable to achieve high performance and fast recovery, the Reorder Ring to achieve log-free transactions, the global index to achieve a globally sorted index as a new level 0 in LSM-tree, the specifically designed PM allocator to achieve efficient persistent memory allocation. Next, I will give the design details for each component. In LSM-tree-based storage engine, the majority part of a Memtable is a range index. Currently, there are 3 typical designs for range index in PM: the fully persistent, the semi-persistent, and the non-persistent. These designs show the trade-off between runtime performance and recovery performance. In the LSM-tree, the Memtable normally keeps a small memory footprint to maintain the optimum LSM-tree shape. So we chose the semi-persistent Memtable design to achieve high performance while keep acceptable recovery time. The index is designed to be volatile and store the pointers to the real KV records. We also add an array to store the selected versions of a key to optimize for MCC feature. The design avoids the full index scan in case of a pointer lookup. We also observe that the Memtable works in append-down writes and batch memory reclaim, so we batch the writes and sequentially process them to reduce write amplification. The next is the design detail of a Reorder Ring. Since the PM hardware supports only 8 bytes atomic writes, it turns out that we have to fall back on log-based approaches for OLTP transactions. Fortunately, we already have the volatile index and the append-down writes in Memtable, which is suitable for the log as data approach to achieve atomic persistence. However, this approach can't be directly used in our system because of 2 reasons. The first is the life cycle differences for records in the log item. For example, the log 1 has records belong to 3 LSM-trees. The flashes or compactions from Memtable to disk cause the purges of the registered records, while the other live records in the log item may prevent to be purged, causing memory space inefficiency. The second is the multi-core scalability problem caused by the sequential persistence of log items. For the first problem, We explicitly persist the records into the related memory space of the text LSM-tree to distinguish the life cycles. And each memory space has its own head to atomically persist a batch of records. However, the OLTP transaction may cover records from different memory spaces, which can't guarantee the atomicity. To solve the problem, we introduced the chain lock and the GIDX pointer. A chain lock item contains multiple batches belong to each memory space and the sequence number. The GIDX contains the current persistence position and the previous one. So we can easily get the last chain lock by scanning the last batch of each memory space. For example, a power outage hits during the persistence of chain lock 3. The last batch fails to update during startup. This inconsistency can be easily recovered. Then we just undo the GIDX of the memory space of the last batch. Another problem is the chain lock item should be sequentially persisted to enable a simple and fast recovery. We give two optimizations to speed up the persistence. The first is the batching to merge small transaction buffers to reduce random writes. And the second is the concurrent ring to control the concurrent writes. The algorithm consists of multiple concurrent buckets, each of which has one leader thread and multiple followers. The leaders harvest all transaction buffers from the followers and merge them as a larger one. So why we call it a reorder ring? In fact, the ring is used to constrain the concurrency, and the reorder is used to guarantee the correct persistence order for chain level items. From the higher level, the chain level items are always sequentially persisted. The leader requests a chain level descriptor from the ring and asks memory space granting. After that, it persists the chain level item, then tells the completion. While in the internals, some phases can be paralleled. We have to reorder them to restore the correct order after the completion of the parallel phases. The next one is the design detail of global index. In our design, the global index works as a new level 0. Because of the byte-addressable feature of PM, the global index just stores the index instead of the whole query pair. The indexes of memtables are frequently merged into the global index. Since there's no requirement for OLTP transactions in such process, so the design can adopt the state-of-the-art persistent B+ trees or other volatile range indexes to enable higher performance. When performing compactions from PM to disk, we create a snapshot for the global index to prevent the store of foreground merges. The last design is the Halloc. Instead of expensive general PM allocators, Halloc is specifically designed for LSM-tree. We create a specific log-free persistent object pools for metadata persistence. Since the memory footprint of this metadata is very small, the memory space for them is statically and continuously preserved to reduce memory fragmentation. The left memory space is formatted into a fixed-size zone object. The zone object is used for semi-persistent memtable in append-only-writes, and also the low-level memory unit for volatile purpose. We evaluate the overall performance with YCSB and TPC-C benchmarks, each for 30 minutes, in the write-intensive workloads of YCSB. The overall performance significantly outperforms the baselines because our solution avoids expensive overlogs, which also brings less write latency. While in the read-intensive workloads, the performance is dominated by slow disk IOs, especially for random request distribution. With the help of a new level 0 and in-memory compaction, our solution also significantly reduces the accumulated disk IOs and the average CPU consumption. For TPC-C benchmark, we integrate our proposal into MySQL Server as a storage engine. With the 80 GB initial dataset, our proposal achieves 2 times performance improvement and reduces the P 19.5 latency by 62%. Thanks.